Anyone who got a ticket over spring break? No? Good. Okay, so we're going to get plenty of donation in the future. And we are now post spring break. So there are a few things we're going to do from this point on. One is we're going to finish the last formal topic, which is merge sort. And so 508 is a parallel algorithm class. So we're looking at the things that are challenging when you write parallel GPU code. And so we talk about how you can do the data extraction for graph algorithms, privatization, and so on. And sort is one of those things that are extremely hard to parallelize. Okay, so that's why we're going to use that as an example of how we can parallelize apparently very sequential, very, very hard to parallelize kind of algorithm. So we're going to do that this week. And then after this week, I'm going to give one lecture next Tuesday, and then I need to go to France to give a talk. So we're going to make a little bit of adjustment here. Because when we set up this schedule, I didn't know my schedule. So we're going to have no class on Thursday, and then when I come back, we're going to have lecture and so on. But we're going to just adjust some of these project work times into the times that I'm traveling, right? So make good use of time, and especially come and discuss with each other, and then use that as a work time to really make progress. As far as the project is concerned, Carl Pearson is here, and so what we would decided to do this semester is that we let you choose between the graph challenge problem, the graph algorithms, and the graph challenge the problems versus the neural net training. So each one has interesting space of algorithm alternatives and the different formulation and different kinds of strategies. So it should be rich enough in either case. If you really want to do both, come and talk to us. But I think it will be wise to pick one of your interest. And if you're a PhD track and you really, really want to do something along your research, we're okay with that, but you need to come and talk to us, okay? Then so that we understand what you're really trying to accomplish, and then try to assess, whether the work is going to get you, to a place where it's going to be a good project, right? So these there are always a little bit of a potential risk. So then you still need to form your team, but then if so these are the things that we need to help you to work out, right? Any questions about the final project at this point? No? Okay. Carl, any comments about the final project?
Yeah, so I think if you're gonna do something related to graph algorithms, I'd be happy to sit down with you and listen to what you think you're interested in doing, or give you some suggestions. I mean, I have more things that I want to try than I can really do myself, so I'd be happy to advise you on it.
Have we posted some of the references?
No, I haven't done that, and I know I owe at least one potential team an email also.
So let's post those on the class wiki so that everyone have access to those references. Okay? Yeah, so yes?
We still have a project write-up due this week?
Yes, I'd like to get something from you. And so don't stress out about that. But we want to know which project you're choosing, and who your team members, and some initial thoughts about how you're going to approach it, right? And then we'll iterate with you.
So it's okay if we change it as we go?
Oh yeah. Or you know what? We only care that you turn in something. Once you turn in, as long as you turn in something, we can look at it and give you feedback. You could get full score, but so don't try to do something perfect 3 days late. Okay, does that make sense? Okay, so do something as much as you can before the deadline, and then send it to us so that we can look at it and give you feedback. Okay. Any other questions? Okay. Yes.
About the schedule.
Yeah.
So The last quiz was quiz 3, but why the next one is
Wait,
quiz
wait,
4?
wait, this is not, yeah, okay.
So the quiz, the last one
Ah,
was
the
quiz
quizzes are still on in the works. I got way too busy with the faculty interviews, so I still need to clean up the quizzes. So we'll post as quickly as possible. So hopefully the exam, the exam is currently scheduled on April 18th. So if we need, what's that?
23rd.
Huh?
23rd April.
Oh, 23rd, yes, because I was going to say, so it seems to be a little bit too early.
Yeah.
So that we would, get you the quizzes, but be way before the exam.
Lab 7 is replaced with the merge sort. There is no neural
Correct.
network.
There's no lab 8. The neural net training is gone, and then it's the merge sort, as the last lab. Okay. Any other all these good questions? Okay.
Where should we submit the proposal?
Yeah. So should we set? Carl, what did we do last time? Did we set up a Gmail account, or did we do some kind of a box account?
The last time I was in it, we took it through Rye, but I think Fox.
No, Compass quiz is good.
We also have a Compass.
I've taught classes at so many times.
So we'll announce it.
Yeah.
Okay.
Yeah.
Okay. All good questions? Anything else? If not, then let's proceed. Question? Okay. So let's proceed with the merge pattern. Where's my? Okay. Hey, thanks, Carl. Okay, good. So when we work on these parallel algorithms and parallel processing, we all know that there are different types of problems. And some of the problems are embarrassingly parallel. Okay, that is, it's very easy to identify, the parallelism. It's very easy to know where to get the parallelism. And then you have something a little bit more challenging. For example, you may need to do some kind of atomic operation. There may be some, some conflicts and so on. So that gets a little more complicated. And then you may have, the situations like the graph algorithms, where in each iteration of your solution, you need to find, where the next data is, right? And then you put them together, and then you get some parallelism. So that parallelism is dynamic, and then it changes. And that leads to some of the loading balance and so on that we can easily get into, that we use dynamic parallelism to try to solve those kind of problems. But here we can actually run into situations where some of these problems are not clear, intrinsically clear that there is parallelism. If you look at the problem definition, some of these problems are quite sequential. So then, how do we, design these algorithms so that we can parallelize them? And the parallelization will also have some cost. So if we're not careful, when we, spend the cost to parallelize these apparently sequential problems, we may end up, introducing too much additional work that we could, end up in negative. We could end up with a slowdown. And merge, sort, in history has been, one of the very challenging problems to solve, because the sorting problem, has, it looks quite intrinsically, sequential, and so, if we want to have a large number of parties participate in, in sort, to parallelize the sort, we could easily, increase the computational complexity and end up with non-scalable, data scalable, parallel execution. So today we're going to learn techniques that are needed for high performance parallel merge sort, and we need to, identify the input for each thread, and then we need to have, tiling for coalescing. We're probably going to go for the first one. Okay, so we'll cover the first aspect, which is the input identification. And then, the next one, next time we're going to look at how we can do tiling, and then we do the circular buffering for data reuse. And in all these things, when we parallelize these algorithms, oftentimes we can get into data use efficiency problems. A lot of times when you try to do parallelism, if you're not careful, you can end up not reusing data as much as you can, especially when the input is uncertain. And this is why I'm teaching this input identification. And then so by the end of the lecture on Thursday, we will be able to to look at a very, very common technique, which is what we call a circular buffer technique, that can increase the data reuse for these kind of algorithms. So we also need to learn how to hide complexities from some of the library users, but that may or may not happen depending on how quickly we can go through the main topics. So if you watch the video, we taught the parallel merge patterns about 2 years ago the first time. Okay. And so there are a few things that I was not quite happy with the explanation. So this time I'm going to make some changes again. So it may be kind of fun to watch the videos from 2 years ago and then and compare that against what we're doing this year, and it may actually even give you a little bit more insight. So let's start with sorting, right? Sorting is one of the very fundamental computer science problems, right? When you learn algorithms and so on, sorting should be one of the basic topics. And there are all kinds of sorting algorithms, but basically first of all what is the definition? Definition is a sorted list goes in certain order. What is non-decreasing order, non-increasing order, strictly increasing order, strictly decreasing order, right? There are all kinds of definition of ordering. So according to an order, if all the elements are satisfying that order in a particular direction, then we call it sorted, right? So here is a very simple example, almost insulting example about what is sorted and what is not sorted. So that's fine, okay. So we also would be talking about how we can merge two sorted lists into one. And the reason why this kind of merging is very important is because oftentimes when we do sorting, we would actually generate multiple, have threads to generate multiple of these sorted sublists, okay? And we'll divide up the work into a lot of sections, and then within each section we sort them so that each sublist is sorted. However, we need to eventually synthesize a fully sorted master list, right? So we will need to be able to take these individually sorted sublists and merge them into a single sorted order list. And that's always the foundation for this divide and conquer kind of approach, where you have a lot of threads to contribute to the work by doing some partial work, and then you have them to quickly merge that into a single solution, and that how quickly you can do this is going to be a very important part of these kind of parallel algorithms. So if you also look at some of the frameworks, such as the MapReduce framework, and you will see that these MapReduce frameworks depend on this kind of paradigm. So that's why sorting is also very important in terms of enabling some of these MapReduce kind of frameworks to in the field. So when we have a partially sorted list, then we can when we assign these elements into the final list, we would need to maintain some kind of requirement. So we're going to talk about the most strict requirement, which is ordered, which is the A and B. A will need to be able to take precedence, that whenever there is a value that is equal between A element and B element that are equal, we need to make sure that the A element goes first. This is sometimes also called stable sorting. So that you maintain, you make sure that all the elements in A will have precedence or priority to get into the list. And this is oftentimes because we may have, maybe these are just tags, okay? And so we may have secondary, things that are being, being labeled by these numbers. So these numbers are, tags for, some kind of content. And we would probably have, a situation where, whenever, whenever you go to the second order, A will be always before B. So even though they are equal in these two tags, you want to maintain a rule that A always will precede B when even if those two elements are of equal tags. So if we enforce this kind of order, then we will go when we merge. This is no question going to be the first element. And the second element, these sevens aren't equal to each other, but the 7 from A should go first, and then the 7 from B will go, and then the 8 will come, and the 9 will come. Again, the 10 from A will come first, and then the 2 10s from B will come, and eventually 12, right? So if you look at this, it seems to be a fairly sequential process, right? So if we look at a sequential sorting function, where did that B come from? In fact, I can tell you exactly where it comes from. On ThinkPad, there's a little pencil top that you move the cursor. Guess what's the key right under this, the pencil? B. Exactly right. So by looking at the slides or the documents, if you see some random little B's in these texts, you can tell that it was composed on a laptop that is what ThinkPad laptop. Okay, this is the classical machine learning. Because the labels, you can actually look for the vectors and then say, that's a ThinkPad, produced on a ThinkPad laptop. Perfect AI. Okay, so let's take a look at this ordered merge function here. This is a sequential function where we take these two sublists A and B, and then we would go through all the elements of A and B, and we're going to maintain 2 pointers. One is going to point into A, and one is going to point to B as the next elements that we're going to place into the into the final list. And at every iteration, we're going to pick either an A element or B element, right, to place into the list. So, and then as soon as we place the element into the list, we advance the pointer for that, for that sublist. And if we finish one of the sublists, then the entire remaining part of the other sublist should go into the list, right? So these are the simple rules. Any questions about that? Okay, so then let's kind of look at the code. So while I is less than the length of A, or J is less than the length of N, we continue, right? Because if either of the two got exhausted, then we just simply take the remaining part of the other sublist and then put it in, right? So for this main loop, we're going to be testing for the condition where we still have elements left in both lists, right? Okay, so when we come to the come in here, I and J are pointing to the next elements of A and element B, element of A and element B that are being considered to be to be placed into the master list. So we look at AI and we look at BJ, right? Look at those two elements and see if AI is less than or equal to to BJ. Remember, as long as the A element is less than B or equal to B, the element should go in. A element should go in, right? A takes precedence, right? So if this is true, we place A, I, right, into the list, into the final list, and then when we bump the pointer for, we bump I, and we also bump K, which is the the index for the next element in the master list, right? The position for the master list to take the next element. Is that clear? Right? Okay. It's very important because we are going to go into something called a co-order. I think it's a co-function. So if this is not clear, that that whole function is going to become a blur. Okay. So you really need to to be very clear about each of these steps, so that the parallelizing function is going to make sense. So if AI is not less than or equal to B, that means AI is greater than B, then B should come in, right? So we would place B into the list and then bump J and K, right? So fairly straightforward. So this is the main loop that is going to, the pointer is going to be just kind of being, the point to the next element. You pick one of them, put it in the main list, you bump that pointer, you bump the position in the master list, and you keep going until you break one of these conditions. If you break one of these conditions, you come out and say, did I exhaust A? So if I is equal to M, that means A is exhausted. So in that case, I will place the rest of B into C, right? So I just keep copying B, into C, and yeah. So that's this little loop of J that would keep copying B into Bj into K, and then bump both indices. But if we exhausted B, then we will copy the remaining part of A, right? So into C, and then after this we're done. So this is a sequential piece of code, right? Any questions? If not, then let's start to look at the example a little bit. So the reason why you also need to be very clear about the sequential code is because the parallel code is actually going to be using sequential code as a component. Okay, the sequential code is actually going to be the bulk of the threads execution, the threads code. Okay, so we start with at the beginning we start with A and B, and then during the main loop we're going to have A less than or equal to B. A0 will be less than or equal to B0. So we're going to copy A into the position, bump the pointer, and then 7 is still less than or equal to 7 in B. So we're going to copy A1 into B1, C1 and bump the pointer. But then as soon as we get to 8, 8 is now greater than B7, right? So now we copy the 7 into the third position 0 of C, and then bump J to 1, and then we bump K to 3, right? So that will continue, and then we say, okay, so as soon as we finish with that 7, now AI is less than or equal to 10 now, so we will copy 8 and bump, and then copy 9, bump I, and copy 10 and bump I. At this point, we exhausted A, right? So the next step is that we copy the rest of B into the C, the remaining C positions, and we're done, right? So it should be very clear now. So if we want to try to do the parallel merge, it's kind of a little bit of a hairy, because for every position of C, okay, for every position of C, it depends on what comes into this. Really depends on the interplay, right? The interplay of the A values and B values. So and until you have done most of the work in the previous positions, it's very hard to figure out what should come into that position. So, we can try to do a parallel scatter parallel. So we have the threads to take, some subset, each thread to take some subset of A and subset of B and try to place them into the right position. However, the difficulty is that if I take a little section here and a little section here, where I start to insert these elements into C depends on the results of the previous sections, right, of A and B. So without doing some of that work, I can't really even tell where to start, right? So there may be some methods for you to do this kind of scatter, but so far nobody has proposed any interesting solutions, right? So if you are interested, in Lab 7, figure out a nice scatter method, and then they'll come to me, and then if you do something reasonable, give you extra credit, okay? So most of the parallel sorting algorithms are gather-based. So I'm going to just now go into the gather-based parallelization. The gather-based parallelization fundamentally will have the threads to be associated with the C positions, okay? And in the simplest form, each thread can be responsible for one position, right? One position. And then it will go into A and B to find, the right element to be placed into that position, okay? But the amount of work it takes to be able to find the element is actually non-trivial. So if we have every thread to go and find the element for, the element for a position, the overhead may be bigger than the parallelism, benefit. So in general, we don't do that, but we do something very similar. We take a section of the C positions and assign it to a thread. So the thread is going to go to A and B and find the little section of A and the little section of B that should go into that little section of C. So we amortize the amount of work that we need to do in order to find the beginning point and end point of these little sections, and use that work to do the sequential merge sort of the A section and B section into this section. So we don't do we don't look for the elements we don't use each thread to only look for the particular element that should go into the position, but we use a thread to identify the beginning point and ending point of a section of A and section of B, so that the work is amortized across all the element positions in C that will be filled in once we found those markers. So finding the markers are actually non-trivial amount of work. So we want to be able to amortize that across a section of these positions, the consecutive positions. Okay, so the amount of the number of positions in each section depends on how expensive it is to be able to find those markers. So let's say if you have a very, very long list that you need to sort, okay, like you have two very long sublists that you need to merge. When you have big sublists, finding those markers in the A and B will take a lot of work. So that's why you will need to have bigger subsections of C for each thread to be able to amortize that work, which makes sense, because if you have a very, very big very big sublist A and B, then you can afford to chop C into bigger sections, because you have so many elements to work with. And so that chopping these things into larger sections will not necessarily take away the level of parallelism you need in order to really get performance. But if the total number of elements involved is small, then you use smaller subsections here, And the amount of work that you need to do in order to identify the markers are also smaller, so that you don't have to amortize it, across as many sections. So each, as many elements in the section. So then you can, maintain more parallelism for smaller lists. So these are the things that you need to, to balance in these kind of trickier parallelization problems. So in this case, I have total of 9 elements that I'm trying to merge. So I'm going to chop the C positions into 3 parts. So 3 sections of positions. And then I'm going to have every thread to go into A and B and find the beginning location and ending location for the little section of A that should go into these positions. And I'm also going to find that little section of B that should go into this position. So if I look at this example, if I chop the positions into 3 parts, for the first part, I'm going to need to have a section of 2 elements of A and 1 element of B that will be going into this section. 1, 7, and 7 here, right? Okay. Now, for the second part, I'm going to need to have all these 3 elements of A, but no element from B to go into this section, right? And then I'm going to have all elements of B to go into the remaining, the last section. So because these sub-lists are already sorted, the section that need to go into any particular section of A or B that need to go into this particular section will be continuous. They will always going to be continuous subsection of A, then continuous subsection of B that will need to go into this. However, how the subsections of A and B are going to be mixed, right, with each other into a section of positions depends, right? So they could be interleaving some way, that I don't know because that's the data. It depends on the data. So now you see that the work that I need to do in order get this parallelism to work is that once I have the positions of each one, I'm going to need to look for the beginning marker for A and ending marker for A for this section, beginning marker of B and ending marker of B for that section, and then I do a sequential merge sort to complete to merge these 2 little sublists into a complete sublist of C. Does that make sense? Any questions about it? Yes.
I did not understand how exactly you determine your end markers for one particular.
Of course you don't, because I haven't talked about it. But do you see the overall strategy?
Yes.
The strategy is I chop my positions into these sections, and then I have a magic. Okay, I have a magic that will determine the beginning marker and the ending marker of each of these little sections of A and B. And then once I have the markers, I have these sublists that I'm merging these sublists into these positions. So the sublist is, or you already know how to merge the sublist, but I have not talked about the markers. You're absolutely right, Vikram.
I mean, I can think of a naive one. I can take whatever the size of the C sublist is and just use the same as my start pointer and end pointer.
That could, it would functionally work. Yeah. But you'll be terrible. Okay. So basically, each output section here will receive its elements. From a continuous subsection of A, and possibly empty, right? It could be empty. Possibly empty subsection of A, and possibly empty section of B. And also, the length of the 2 subsections of A and B will add up to the length of the subsection of C, right? So those are the properties that we know, okay? So if I summarize, each thread gathered the elements of a continuous section of the output A, and it is corresponding from one element per thread. And all the threads identify the starting and ending locations of the continuous subsections of inputs A and B. They will be examining in parallel, using or examining in parallel. And the input, this is the input identification and partition. So where you're going to extract your input, right? This is also a form of input extraction, right? Where your input will come from in a bigger data structure needs to be done with some work, and Vicon doesn't know how to do it yet, right? So that means that it's non-trivial. If it's trivial, Vicon would already know, right? So that's a kind of a validation that this is worth a paper. In fact, this was a paper many years ago. Okay, someone wrote that paper about how to do the markers. So all the threads perform. Once you have all the markers, then all the threads can just perform the merge sort on their individual section. And then, all the sections together will form the correct final merged list. Okay? So, for thread, we have three threads, thread 0, thread 1, and thread 2. And then, so for thread 0, we're going to need to identify those markers. So the beginning marker of thread 0 is trivial.
Yes.
0, right? It starts with 0 location. It cannot go anywhere else. Starting location, the marker for B is also 0. That's quite trivial. However, the question is, where does it end? Okay, where does it end? So this, knowing that the first thread will end at the location 1, or you can say it ends before location 2, is the work, okay, that we will need to do. But if we know that we're 2 marks, 2 is the position after the section, then we know exactly what this is, because the number of elements of these 2 lists need to add up to 3 here, right? Need to add up to the size of the C section. So as soon as we find the ending marker for A, we know exactly where the ending marker of B is going to be, okay? And so in this case, if we know that I is 2, then B is going to be 1 right there. So B equal to 1 means that the section is all the elements before this position. So that's going to be 7. So the way to figure this out, okay, now I'm beginning to work into that magic function here. The way to figure it out is that we're going to try to increase A. Well, increase A and B, adjust A and B until we see a phenomenon where if we increase A by any more, okay, if we increase A by any more, then it will be bigger than B, right? So remember, these 2 numbers need to add up to 3, right? So if we increase A any further, B will need to be decreased, right, in order for them to fit into that section. So the ending position of B, it would need to be such that the B element is still going to be, greater than A. Now, if we increase A by too much at some point, it's not going to, the property is no longer going to be held. So we can, keep trying to do this. If I increase A by another 1, which is 8, then B will have to be 0. But the problem is this 8 will come in before that 7, and that's not good for the final ordering. So if A is decreasing anyway, let's say if A is decreased into this position, then we're excluding 7. But then B will have to increase to 10, right? So if A only has 1 element, then B will need to have 2 elements. But in this case, 7 will not get into the list, and 10 will get into the list. So then you have a problem with final ordering. So you have a sweet spot at some point where if you decrease or increase A or the pointer to A or B in any way, you would become incorrect. So then you settle on that particular point. Okay. So same thing, with this one. So for this one is a little bit trickier because you cannot assume the work of the previous thread. Otherwise, it's not parallel, right? So it would be nice if we say, okay, I know where the previous section ends for A and B for the previous thread, and then I build on it and then look for the next marker, right? That would be nice, but then you go back to sequential algorithm. So the next one essentially will say, I'm going to have a effective section of 6. And then I'm going to start with 0 for A and start with 0 for B. And then I'm going to look for that, that position. So, the position of the end marker in A and B, right? So that will be, the work that effectively what we're going to do for thread 1. And thread 2 is going to say, I have a sublist of 9, and then I'm going to look for all the marker position and marker position in A and B that will give me the 9, right? So if I do this, then I have parallelism, but I have a kind of a loading balancing problem.
Yes.
Because the later threads are going to be having to look at more and more of the A and B elements in order to be able to find those markers. So they will become slower and slower, right? So but think about this. When we do this, finding the markers is a search problem. Okay, it's a search problem. And search problem in a ordered list, right? We're searching in 2 ordered lists. When you take something like 374, when you have a search in an ordered list, what do? Do you do sequential search? You do what? Binary search or n-ary search even, right? So if you have bigger, the even bigger amount of elements, you may want to do n-ary search, right? So so this is the part where you can use binary search for just so that you can do the NP. But in general, you may want to even have some threads to do quadary or fornary search, right? Or octary search or something, right? So that would be a fancier way of organizing your kernel, so that the higher the sections you go, the higher order of the search that you'll be using, right? So that's the general idea. We're going to just accept the fact that each thread in the increasing higher position sections in the C will need to do more search. It will need to search through a bigger list, and then we're going to use the strategy to mitigate that. And so basically, this is the example where you should use to convince yourself that when you have the first section, you have 3 elements. Then we find these markers, and the second section is these really equivalent to these 6 elements, and then you start with 0 and then you go. However, you can cheat a little bit. You don't have to always start from the beginning, because you know that you need to have at least 3 elements, a total of 3 elements from A and B that will need to go to the first section. So when you search for your ending position, it cannot be anywhere earlier. It cannot be less than you don't have to go all the way to the beginning. However, that's a heuristic, and in some cases because you could have a situation where all the elements come from B, then you do need to go from the beginning. So you need to have a way to go back to the beginning if necessary. Okay? So you're going to see all that in the search strategy. Does that make sense? So you try to do as little work as you can by moving the window a little bit higher, looking for that the ending point, but you may need to go down to accommodate the situation where most of the elements ended up coming from the other sublist. So there's something called co-rank, a rank, and then we'll talk about rank, and then we're going to be talking about co-ranking. Okay, so this now is the magic function. Okay, so if we have a prefix scheme, a prefix string leading to the case element. So let's say from this element here, we have a string leading to this element. So this element is element 5, right? 0, 1, 2, 3, 4, 5, element 5. So the string that leads to element 5 has a rank of 5. Okay? So that's the simple definition of the rank of a prefix string. In fact, when you look at this, you will realize that we learned about prefix a while back in 408, prefix sum, right? So prefix sum is about adding up all the prefix string, right, up to the element. Sometimes inclusive, sometimes exclusive, right? So that was prefix sum, and we also call it scan, right? So here we are going to be interested in the prefix string leading into the section, the prefix string leading to the ending point of section of sublist A and this section of this B. So because we're going to need to find both markers, we're going to use a concept of co-ranking. Okay, co-rank means that you're going to find a prefix of A and a prefix of B, but then the length of those two add up to a particular number that you're going to look for. So what's that number from? If it's thread 0, it's going to be 3, okay? And if it's thread 1, it's going to be 6. It's really, the rank that you're looking for is the element that is right after the section of position you're responsible for. So that's the rank, that total rank that you'll be looking for. But then the two prefixes that you're going to look for will have, when you add up those two ranks, the length of these two strings, they will add up to that number. Okay, that total number. So that's why it's called co-rank. Co-rank means that I'm looking for two substrings whose length will add up to a particular number that I already know, right? But then I don't know if this string is going to be longer or shorter, or the other string will be longer or shorter, right? So when one gets longer, the other one goes shorter, and vice versa, right? So that's why it's called co-ranking, because once you determine one, you know the other, right? So they all need to add up to 6 in this case. And then, so if one is 4, and you know the other one is 2. So that's why it's co-rank, okay? So we're going to be writing a co-ranking function, to make that decision. So the definition of co-ranking is that of a prefix string leading to the case output element is a pair of I and J. So I and J are those two, two markers, right, into the A and B substrings, strings, and then the prefix strings of A and B that are used in forming the output of prefix string. So, I and J will need to add up to K. Okay, I and J will need to add up to K, and then A and B, but then you need to satisfy this property, where if you look at I minus 1, okay, I minus 1, it has to be less than or equal to bj. And if you look at j minus 1, bj minus 1 has to be less than ai. And this means that you can no longer, you cannot adjust I or j to any smaller. Because if you adjust I a little smaller, j, remember j has to go up, right? And then suddenly the element, one of the elements of B will get into that sublist that shouldn't be there. Because the I element should be there, right? And vice versa. If you make the I element a little bit small, index a little bit smaller, and then suddenly you need to increase. If you make the I index a little bit smaller, you get another element of B in there, but it shouldn't be there. If you get a J index a little bit smaller, then you need to get one more A element in there, but that element shouldn't be there because the original J element should be there, right? So that's why as long as you can satisfy this this relationship, you can I plus J equal to K, okay, and you have both of these conditions true, then you found your markers for the J list. This was a paper, okay. Many years ago, someone wrote a paper about this, okay. You were born a little bit too late. Otherwise, you could have written that paper. And that paper has thousands and thousands of citations because, all the merge sort kind of techniques are based on that work. Okay. So, but there are many other things to show, right? Many other things to prove, many other things to build. So, don't despair. You can still get your PhD, you can still, become famous, you're still going to have thousands of citations. Trust me. Okay? So, so this is just an example where for I0, I'm going to I can just do something sequential. I can increase A and B. I can increase A and B so that I say okay, I'm going to start by guessing, right? Guessing that let's say I need to have one element of B A and then two elements of B. And or half of the elements will come from each one, right? Something like that. And then I adjust. I increase A until I violate the condition. And then I say okay, then I can no longer increase A, and so and then I check if B also satisfies the equation. If B does not. If I can increase B any further and decrease A a little bit and still satisfy the property until I can no longer increase B, then I'm done. Okay, so I can I find my locations. But if I'm not careful, I will be sequentially searching through this quite a bit. So I need to use some kind of binary search or n-ary search in order to be able to do this quickly. Okay, quickly settle into the right range and settle on the right markers. Okay, so I give you the second one and then the third one for an example. So we use the binary search for I and j values to minimize the effect of increasing the search ranges. And so once you understand that you're really looking for the finishing marker of each section, and theoretically you really need to search through all the previous the substrings anyway. So that's why you're going to have bigger and bigger overhead for the sections. So now that we understand what it is, we can define this co-rank function. Okay, so this is really the most important part of the parallel merge sort. Finding the ending marker for A and B that you can for each section. So in reality, what we actually do for each thread is not just to find the ending marker of each section. It actually finds the ending marker of each section and the ending marker of the previous section, right? So that you know the exact range. Because even though another thread is calculating the ending marker for the previous section, you cannot depend on it, right? So that's why all the threads will be calculating the ending marker of the previous string, and then the ending marker of the current string, and then you clamp the section of A and section of B, right? So you will see that in the kernel of that code. So when we come into the co-rank function, we're given the input parameters k. K is the ending marker of the C, right? Of the C section, that K, right? And then A, pointer to the entire A array, right? Pointer to the B array, and then the number of elements in A and B, right? The number of elements. So M is the number of elements of A, and then N is the number of elements in B, right? So these are all the information you need in order to calculate the ending markers of A and B. And also, because we know that we're looking for the co-ranks for K. So K is given to you by the caller, right? So all you really need to do is to return either I or J value. Because the caller knows K value. And if you return the I value, the caller can just do a subtraction and get a J value, and vice versa. So the function only needs to return one of the I and J, and the caller knows exactly what to do with it. You don't have to return two values. Does that make sense? Mathematically, this is beautiful, right? And coding-wise, it's kind of trivial. So I'm going to start by setting the I value to something like the mean value of between K and M. Okay, so this is a heuristic now. Remember that heuristic I was talking about? I'm trying to not to start from both lists from 0, right? So so theoretically, what I can do is I can start at the beginning of A, right? So I can set I to 0, and then set B to be K, right? They need to add up to K. So I can set I to 0 and B to K, or vice versa, right? I can do either way. But instead of doing that, I'm going to see if K is is less than M. So the reason is if K is greater than M, okay, if K is greater than M, then you know that going back, if K is less than M, okay, if K is less than M, then I can just start by setting the marker to be in A to be K, right? Because I know that at least I need to just assume that the first K elements in A will all go into the final version. It's just a heuristic assumption, right? But I don't need to go any further than that, because I shouldn't have to look for any more elements than a K, right? I only need K elements. So if everything goes from A into the C list, then the first K elements will do it. So if M is much, much bigger than K, then I don't need to go and look at any of the elements beyond that K in list A. Make sense? Okay. You had a question? Okay. No question. Okay. But then if K is greater than or equal to M, then you say, okay, so K is bigger than the list of A, right? But no matter what I do, I cannot take more than n elements into C, right? I only have so many elements in A, so I just set the ending point to the end of A, right? So those are the two settings. Whatever I do with I, I just subtract I from K and then give it to J. So at any point in time, I'm going to maintain the property that I plus j is equal to
Okay.
k, right? So that's the invariance that I'm going to to maintain. So I also will set two markers called I low and j low. Okay. So I low means that it's really the maximal between 0 and k minus n. So whenever I start, I assume that if I took anything, everything from B. Okay, so let's say if I'm going to take anything from everything from B list, right? And that's the sort of the worst case for in terms of the number of elements that I'm going to get from A, right? So if I can assume that if I start from a position that is